Good afternoon, all of you. Welcome to this first session of Open Channel Flow module. And in this particular module, uh, we'll concentrate on uh, flow through open channels, and mostly that is free surface flow. Okay, what is this open channel flow? Uh, this module will introduce the concepts related to flow through open channels, where the flowing fluid is a liquid forming a free surface at its top having atmospheric pressure. So, the points which are important here is that open channels, free surface and atmospheric pressure. These three are key phrases here. If we talk about natural system, where we can see channels and canal. This is a river channel in a common irrigation system, where we have a diversion structure, and through this diversion structure generally water is diverted into the canal system, where there will be a canal head regulator, and through this main canal and branch canal system and distributaries, water will be transferred to the uh, individual fields through this water course and outlets. There can be minus and field outlets within the system. So, in this course, what are our module objectives? To explain the characteristics of open channel flow, involve the concept of most economical section in open channel flow, to distinguish between different types of open channel flow based on their spatial variability, to apply the concepts of specific energy, specific force and critical flow in open channels. What are the units? We have total 6 hours. So, I have divided it into 5 units, and 6th unit, that will be the module level problems. Unit 1, uh, that is for characteristics of open channel flow and channel properties, it will have unit level problems. Unit 2, uniform flow and most economical open channel cross section with unit level problem. So, first session will cover these 2 units, and uh, for rest of the 2 sessions will cover this 3 to 6 units. What should be the learning strategy? Learning strategy, mostly reference books, engineering fluid mechanics, uh, and uh, you can go through this chapter 15, flow in open channels, mechanics of fluids, chapter 10, flow in open channels, and 2 Indian author books, that is flow in open channels by K. Subramania and flow through open channels by Rajesh Srivastava. So, let us start the first unit, uh, that is characteristics of OCF and channel properties. What are the objectives or unit objectives for this particular unit? To explain the characteristics of open channel flow and to compare them with pipe flow under pressure, and to identify the important properties of open channels. So, what is this? Liquid flow forming free surface at the top where atmospheric pressure exists is called open channel flow. What is this free surface? Free surface is the interface between an upper layer of water and air. So, free surface word is important here, and that is related to open channel flow. This is a typical natural channel, and in this one, if we check the velocity distribution at any particular cross section, then you can see that these are velocity contours, and this velocity contours, there will be variation, and you can also see the secondary currents there, and you can from theoretical perspective, near boundary the velocity should be 0, and as it will move towards the central portion, the velocity will be maximum. Uh, so, the average velocity that can be estimated with this formula, that is 1 by A and integration V dA. What is this? This is the average velocity in a particular section, and A is the sectional area, and V is corresponding to each elemental sectional area, and if we integrate this, we can get the average velocity. Now, velocity uh, is 0 uh, at solid boundaries, and gradually increases with distance from boundary. So, in this case, the average velocity we have represented in terms of this integration sign. Variation uh, is in longitudinal direction and lateral direction. So, variation can be in a longitudinal or lateral direction, and we are talking about either prismatic or non-prismatic channels. So, this can be either man-made or natural ones, and mostly our concern is flow due to gravity. Uh, and in this uh, prismatic channel, uh, we are considering the cross sectional shape and size that is constant, and non-prismatic channel, which are mostly natural channels, you will not find the sections we uniform in nature. So, this velocity distribution in channels, uh, there will be much variation in that. So, mean velocity that we can calculate based on the velocity variation in cross sectional area, we can also see what is the variation along depth. So, mean velocity, it is defined for the entire cross section on the basis of longitudinal component of the velocity. So, this V is actually longitudinal component of the velocity, and y naught is the total depth. But interesting part is that this is your free surface, and maximum velocity is just below this free surface. So, why this maximum velocity is below free surface? This is due to the secondary currents, and it also depends on the aspect ratio of the channel. Aspect ratio means aspect ratio, that is ratio of depth to width. In narrow channels, narrow channel, this dip will occur much below compared to a wide channel. In wide channel, this dip will be much near to the surface. Then we will talk about this energy correction factor. The kinetic energy for this elemental area is defined as this is the rho V dA, this is the mass, and mv square v square by 2, the total area, the kinetic energy flux is computed. So, in this case alpha is the correction factor because we are utilizing this mean velocity. So, what is that correction factor? The correction factor is nothing but the ratio of these two quantities. So, alpha represents the ratio of the actual kinetic energy over the cross section to the kinetic energy computed on the basis of average velocity. Obviously, if we are considering the longitudinal component of the velocity, there will be some amount of error associated with that. We need to correct that. So, alpha we can think as correction factor which is corresponding to the energy. Similarly, we can correct the momentum, in this case m into v, and beta is the momentum correction factor, where this beta represents the ratio of actual momentum over the cross section to the momentum computed on the basis of average velocity. Now, we will talk about this open channel, and let us define different terms. This line we can consider this as datum, and from datum this point, the first point or point number 1, that is z distance, and this is the elevation head of this point. At the same time, this p by gamma is the piezometric head or pressure head corresponding to that, and the velocity head which is associated with this section, we can say that the velocity head is v1 square by 2g, and alpha 1 is the corresponding correction factor. So, from Bernoulli's equation we can write P by gamma, which is the pressure head plus velocity head alpha 1 into V1 square by 2g plus Z1 is the elevation head, and if we compare the second section, Z2 is the elevation head, P2 by gamma, this is the piezometric head, this pressure head, and this is the velocity head. Again alpha 2 is the correction factor for this particular section, and HL is the head loss. So, HGL is the hydraulic gradient line which is corresponding to the piezometric head. Piezometric head means that pressure head plus elevation head, and energy gradient line which is the total energy line. So, total energy line here will be with the elevation head, pressure head and velocity. So, the difference, that is the head loss, and head loss can be represented as SF. SF is the energy slope into distance, should be del x between two points. 2 points, this is the distance. Now, this open channel flow is different from the pipe flow. What are the differences? In the pipe flow, this is the uh, pressure head, and this is the pressure head here, this is the hydraulic gradient line, this is the energy gradient line here, and this is the datum, these are the elevation heads. So, in this one, conduit is completely filled with liquid, and open channel flow, liquid forms a free surface exposed to the atmosphere. In pipe flow, hydraulic pressure gradient causes the flow. Here in open channel flow, gravity causes the flow. What are the other important points? Generally, conduit is circular in cross section, and channel can have any cross sectional shape. This is hydraulic gradient line indicates piezometric surface, the sum of pressure head and datum head. This hydraulic gradient, this indicates the free surface. This is the sum of the flow depth and datum head. Pipe flow and open channel flow, maximum velocity occurs at the center of the conduit. In open channel flow, maximum velocity occurs slightly below the free surface. In case of pipe flow, the conduit can be used as open channel when it is not running full. Open channel cannot be used as a conduit. So, these are man-made canal system. Generally, this are the man-made systems which are lined ones, and in this lined canal system, shapes are of prismatic in nature. So, what are the channel properties? Channel properties for any rough section, this is some irregular cross section, and irregular cross section will consider this as a free surface. So, we will represent free surface like this. Now, in this free surface, let us say this is the depth of the flow y. So, what is the weighted perimeter? Weighted perimeter is is the perimeter which is corresponding to a particular depth of flow. So, weighted perimeter in this case is the perimeter which is associated with depth. So, this part, which is the weighted part of the cross section, can be called as weighted perimeter or P, and cross sectional area is A. So, hydraulic radius or R, will call it as A by P, and if this part is the top width or T, then we'll use this term, that is hydraulic depth or D. This is RH and DH, this is A by T. So, for simple rectangular cross section, where y is the depth of flow and b is the width of the channel, we can say that this A is b into y and weighted perimeter is b plus 2y, and in this case the top width is equal to the width of the channel. So, this hydraulic radius in this case is A by P, or this is By by B plus 2y, and hydraulic depth is A by T, or this is by B or y. That means for rectangular channel cross section, this hydraulic depth and depth of flow is same, but hydraulic radius is different. In this case, um, we can uh, introduce another concept which is called as Froude number. Basically, this Froude number uh, is the ratio between the inertia force by gravity force, and gravity component here uh, that is important, and this Froude number is defined as velocity or average velocity divided by root over g into this hydraulic depth or A by T. So, velocity we can represent it in terms of discharge by area. For any steady state incompressible flow situation, we can write this as Q is equal to A into V. So, where A is the cross sectional area and V is the mean velocity. So, we can represent this V in terms of Q by A, and D we can represent it in terms of A by T. So, finally, we can get this expression for Froude number, which is Q square by T GAQ, and using this Froude number uh, we can define different types of flow. One or first one is subcritical flow, that is Froude number is less than 1, where the flow moves slower than the gravity waves. Supercritical flow, where Froude number is greater than 1, moves faster than gravity waves, and critical flow, where the Froude number is equal to 1, move at the same speed as gravity waves. Surface gravity waves move at a speed of root over GD, where D is the hydraulic depth. So, based on this classification, we can uh, define different types of open channel flow. So, what is this subcritical and supercritical flow? Subcritical flow is tranquil flow and supercritical flow is rapidly varying flow. If we have a gate on the upstream section, we have subcritical flow. This is the EGL, and at the downstream end we have supercritical flow. So, obviously, in this case the velocity is less compared to supercritical flow. That is why this Froude number is less than 1 in this side it will be obviously greater than 1. Near to gate, this is touching, the water surface is touching this EGL, because the velocity at the gate, that is 0, fluid velocity at gate, it is 0. So, we can now discuss different types of open channel cross sections. So, rectangular cross section we have already discussed. This is rectangular one. Then we can consider the triangular cross section. Triangular cross section, if we have triangular cross section, let us say this is the free surface and this is the total depth of flow y, and we have different slopes. One is to z, the slope of this sides, and we can define this top width as T. So, in this case we can write the area A as half, this is the base. So, base will be y into z, 2 in y into z, this is z. So, this will be yz, this part. So, this part, this total top width, that will be 2 yz into y. So, this will be z into y square. Then what is the weighted perimeter P? P is this minimum part is 1 plus z square. This is a total thing is 1, this is y square plus y square z square, this is square root and 2, and we can take out this y. So, we can write it as 1 plus z square. Thus, hydraulic radius RH in this case, that is A by P or yz square divided by y 1 plus z square, and top width T is 2zy, and hydraulic depth dH, this is A by T or zy square divided by 2zy, that is our y by 2. So, if we have equal slopes on both the sides of triangular cross section, then we can see that hydraulic depth is just half of the flow depth, and top width is 2 times zy. Z is the slope associated parameter of the sides. Now, we can talk about this trapezoidal section. Trapezoidal cross section. In case of trapezoidal cross section, this T is the total top width, Y is depth of flow, this is 1 Z slope related parameter side slope, this B is bed width. So, in this case we can divide the cross section into triangular part 1, triangular part 2, and third one we can write it as rectangular cross section. So, in this case the area is P plus ZY into Y. So, B is this part or width of the middle portion, and Y is the depth. So, we are considering this area. Again, another part, that is 2 into ZY, because it has got this part and this part, and Y, this is actually ZY into Y. So, weighted perimeter P in this case is B plus 2Y 1 plus Z square. Top width, so hydraulic radius B plus ZY into y divided by b plus 2y 1 plus z square. Top width T is b plus 2z y and hydraulic depth is b plus zy y divided by b plus 2zy. Similarly, the last part that is parabolic cross section. Parabolic cross section, we can determine the values, but here some of the parameters or some of the equations are a bit complicated. This is T is the top width, this y is depth of flow. In this case, let us consider our coordinate system which is in x direction. So, and this is, let us say, capital Y. So, we can represent this capital Y as a into x square, and if we are considering the total depth of flow or y, so y is nothing but a into t by 2 square. T is the top width. So, half of top width if we consider, then we can write this full flow depth thing, and this is actually y square root this is 2. So, top width is root over y by a, and this thing. So, what is area? Area is 0 to y, this x and this dy. So, in this case, this is 0 to y, and what is x? X is root over capital Y by a, and this is dy. So, we can represent it as 2 by 3 y to the power 3 by 2 root over a. So, from this one we can write this 2 by 3, and from here this is 4 by 3, and this part we can write it as 2 y by root a into y. This is nothing but area equal to 2 by 3 t into y. This 2 I have multiplied here because we need to consider both the parts, or we can directly write this as 2 into. So, in this case area we can write it as 2/3 Ty weighted perimeter is the most important part here because it is mostly implicit in nature. So, why? Because in this case we need to determine the length of this curve in this particular problem. So, weighted perimeter we can represent it in terms of dy by dx square plus 1 and this whole to the power half into dx. If we integrate this, uh, so we can get something which is y by a, and this is 4 a square x square plus 1 dx. This is implicit integral. If we get the exact expression for this integral, we can get the weighted perimeter. So, we can see that we have increased the complexity of the problem. Depending on the complex nature of the cross section, we need to determine the weighted perimeter. This is hydraulic radius. So, A by P will be the hydraulic radius. The stop width or T, again this will be 3 by 2 AY, and this hydraulic depth or D, uh, this is the ratio between these two. So, this is 2/3 of Y. So, we can see that uh, for complex cross sections also we can find out what will be uh, the nature of your perimeter, and we can find out the length, and from this we can find out the channel properties, that is hydraulic radius, hydraulic depth, and we will be utilizing these hydraulic depth and hydraulic radius in the next unit to get the velocity, uh, the expression for velocity. So, now let us talk about this circular cross section. In this circular cross section, uh, things are similar, but in this case we can divide this circular cross section into two parts. One will be this triangular portion, another one this arc portion. So, we can uh, get uh, this value of the area which is half r square theta. R is the radius. So, in this case this will be d naught square by 4, half into d naught square by 4. So, we can get this area. Similarly, we can get this perimeter. This is S is equal to r into theta. This is the theta, and radius is d naught by 2. So, approach is same. We need to divide the cross section into different parts, or if it is not possible, we can get the parameters by integrating different parts. So, let us talk about this unit level problem. This is a simple unit level problem where we are considering the velocity distribution. In this case, uh, the velocity distribution in a rectangular channel of width b and flow depth y naught was approximated as v equal to k1 y to the power half, in which k1 is the constant, and calculate the average velocity for the cross section and momentum and energy correction factors. So, what is the area? Area of the cross section is b into y naught. What is the average velocity? Velocity is v, capital V, equal to 1 by area, and this thing is applicable for b into dA. dA is again b into dy, that is elemental cross sectional area. In this case, single integration is sufficient because there is no variation in the width. So, only variation is in terms of depth. So, we can vary the integration limits from 0 to y1. That means, from bottom where the depth of flow is 0 to the top where our depth of flow is y naught. So, in this case, b that will cancel out 1 by y naught, and 0 to y naught v, this is 1 by y naught, 0 to y naught k root over y. So, in this case, this will be y to the power 3 by 2 by 3 by 2, that will be 2 by 3, and y naught that will cancel out. So, finally, it will come to this k1 y naught square root. Similarly, if we try to get this kinetic energy correction factor, again we can use this integration thing 0 to y naught v cube b into dA dy, that is total dA. This is k cube, and this will be y to the power 3 by 2 if we perform integration and just compare with this expression, we can get the value which is 1.35, and momentum correction factor, which is square term here, that will be giving you 1.125. So, this is the velocity uh, for a known uh, distribution. What if do not have any information about the cross sectional area? Then we can consider this velocity as mean velocity, and we can utilize it for our calculations, but we will consider this that alpha and beta values are equal to unity, that means equal to 1. But if only if there is no information about available about the system. Second problem, water flows uniformly covering half of the cross section in a circular concrete pipe of diameter 0.8 meter. Find the hydraulic radius. This is the total depth or total diameter of the circular section, and this is the depth of flow, which is just half. In this case, total cross sectional area, that will be half of your pi by 4 0.8 square. 0.8 is the diameter, So this is 0.251 meter square. Weighted perimeter, that is half. Uh, this is 2 pi r. The half will be there, and this is hydraulic radius, that will be area by perimeter, that is 0.2. So with this we are uh, finishing this unit 1, and after this we will start this unit 2. So welcome to this unit 2. First of all, I would like to answer the queries that I have received in the chat. So first concept is related to uh, pressure head. Why we take pressure head as a depth in open channel? Let us consider this part as our free surface, and this is as channel bottom. Then this part as datum. So if we take the channel bottom portion, then this is our elevation head Z. Then one part will be pressure head. Pressure head is P by gamma. That is usually known part we generally utilize in our Bernoulli's equation. So in open channel flows, in simplified form, we consider that pressure distribution, that is hydrostatic. That means at the surface it is 0, and as we will move towards the bottom, or towards the bottom of the channel, the values will increase. Obviously, there will be linear variation of pressure. That means starting from 0, if the depth of flow is h, then gamma h will be the equivalent pressure that will be experienced at the bottom. Now this pressure head is P by gamma. We can write this pressure as gamma h divided by gamma. So this is head, or this is pressure head, and this is depth of flow. Thus these two quantities are equivalent. Okay. I hope this answers your queries. Next one is related to the secondary current. Secondary currents are usually, if this is the cross section, then within the cross section you will have different components. One will be longitudinal component, then there will be transverse component and other components. But in general we consider the longitudinal component of the velocity, but if we closely look into this channel cross section, you will see that there will be very pressure velocity variation in terms of these contours, but there will be generation of vortices within this cross section. These are called as secondary currents, and in this particular module we are not considering this secondary current part. Another question is whether the cross section we consider it as uh, wide or narrow. So wide cross sections, we can say that your hydraulic radius will be almost equal to or equivalent to the depth of flow. Then we can characterize the channel as wide channel. Another question we have received related to gravity waves. Uh, uh, Although it is not part of this course, but we can say that if we drop a stone in still water, then a surface wave will be generated, and it will take some time that wave to the rest position, and that wave we can consider it as equivalent to gravity waves, okay, and surface gravity. That is the simple definition. Okay. Now we can start our lecture 2 or unit 2 in this uniform flow and most economical open channel cross section. What are the unit objectives? Although one objective is written here, to develop the concept of most economical open channel cross section based on uniform flow formula. So, this term uniform flow is important. In our lecture 1 we have only considered flow, but whether it is uniform, non-uniform, that we have not discussed. So, let us classify this open channel flow based on this steady and unsteady conditions. What is this steady thing? Steady and unsteady. In steady flow, we consider that your flow properties are not changing with time, but unsteady flow condition we generally consider, we should consider that your flow properties are changing with time. So, this is time independent, this is time varying. Now, let us talk about this term which is uniform flow. In case of uniform flow, your properties are constant along the length of the channel. That means, in steady and unsteady case, we are talking about time concept, and uniform flow we are introducing this space concept. So, in this case, properties are constant along the length of the channel. Properties can be your depth of flow, maybe velocity. These quantities are not changing with your uh, length of the channel. Now, in this steady flow, it can have steady, gradually varied flow, and rapidly varied flow, and third one is spatially varied flow. So, in this gradually varied flow, we'll consider the flow condition where the curvature of streamline not excessive. The curvature of streamline not excessive. In rapidly varying flow, we'll consider that depth changes or flow depth changes appreciably over short length. So, gradually varied flow, common example is flow in our laboratory scale flume, and rapidly varied flow example is hydraulic jump. Within a short length there will be change in flow depth, and specially varied flow, in this one some flow added to or abstracted from the system. That means in this case either some flow is added to the system or some flow is abstracted from the system. So, in this first two cases, that is gradually varied flow and rapidly varied flow, uh, in this case we will consider that no flow is externally added. That means no flow is externally added to the system or abstracted from the system in first two cases. And spatially varied flow, if there is addition or abstraction from the system, then only we will call it as spatially varied flow. So, combinations of free surface flows. We have seen that steady term, it represents time, and uniform term, it represents space. So, we can have steady uniform flow. So, where velocity is constant, y is constant, that means mean velocity that will be constant, depth of flow that will be constant, steady non-uniform flow. Steady, that means it is not varying with time, but varying with space. That is why Vx and Vy. V velocity is varying with x and depth of flow that is varying with x. That is why it is non-uniform flow, steady but non-uniform. Another case is unsteady non-uniform. That means unsteady means it represents time, that means time varying quantities, at the same time space varying quantities. So, velocity is a function of space and time, that means v as a function of x comma t, y depth of flow that is x comma t, that means y is also varying with space and time. But another case where we have this condition unsteady uniform flow. Unsteady means there is no variation in time, but variation in space. There is no variation in time, but variation in space. This is almost impossible in case of open channel flow. That means V is only function of time. Yeah, uh, V is function of time, Y is function of time. Unsteady non-uniform flow, this is the most general condition for open channel flow, and practically this is the situation. If you consider any river channel, there you will find that there is variation in your cross sections. At the same time, depth of flow will be varying spatially and temporally. So, most of the condition or most general condition is unsteady non-uniform flow. But this unsteady uniform flow, this is impossible in case of open channel flow. This is possible only in case of pipe flow which is connected with reservoir. Let us consider unsteady uniform flow. Unsteady uniform flow means that velocity is a function of time, depth as a function of time. Let us consider one simple reservoir or water storage tank, and a pipe is connected to that. So, this is free flow at the pipe end. So, initially we can connect it to pump and we can fill this reservoir. So, obviously velocity at this level will be determined based on the varying head. So, flow in this part of the pipe, we can consider this as unsteady, but within this section length there will be no change in pipe your fluid velocity with space, because if there is reduction in this height, so obviously velocity will reduce in this case. That means velocity is varying with time, but in this case velocity is not varying in this section. So, in OCF or open channel flow case, this situation is not possible. Only in case of pipe flow connected to a reservoir this is possible. So, this is not possible for OCF condition. So, comparison of between this uniform, non-uniform open channel flow. So, let us say that this is our bed level connected to a system. Let us say you have some elevated hydraulic structure, flow over that, and initially you have discharge Q. So, you can see that there is non-uniformity or change in the velocity profile near to this plane section A to B, but B to C there is uniform flow. Again there is rapidly varying flow. In this case this is non-uniform flow, but there is gradual variation in the water depth, and intermediate portion we have uniform flow, and rest of the section there is sudden jump in water level. So, this is uniform flow, non-uniform flow, and we will call this type of flow as rapidly varying flow. This is gradually varied flow, this is rapidly varied. This example is steady flow over spillway. So, steady uniform flow. So, obviously there will be no change in the velocity profile. So, velocity profile in two cross sections, that will be same, depth of flow that will be same. In this case we are considering rectangular cross section. So, that is why width is same. So, uniform flow, uniform open channel flow. In uniform open channel flow, all the flow properties remain spatially constant. Thus, in this case your energy slope is equal to your bed slope. This is important assumption here. If we consider Chase's equation for open channel flow, Chase's equation for open channel flow, Chase's equation for uniform open channel flow. You already know that V is our cross sectionally averaged cross sectionally averaged velocity. So, V is 1 by A dA. We know that head loss can be represented as FL by D V square by 2G. In case of open channel, will represent it, D can be represented in terms of 4R, and this is V square by 2G. This L is the channel length, and F is the friction factor. So, in this case, if we represent V in terms of other quantities, so we can write this 8 G by F root R and this HL by L, then we can write the equivalent expression, which is C root R into S. In this case, uniform flow, this SF or slope of the energy slope uh, or an energy gradient line, that will be equal to bed slope. This is the uniform flow condition, and for calculation of discharge we can just only multiply A with this one and we can get this C is known as Chase's coefficient. Chase's coefficient. So, next equation we will consider this Manning's equation for uniform open channel flow. So, this is the most popular uniform open channel flow equation, and in SI system we can write V equal to 1 by N R to the power 2/3 S naught to the power half, and N is the Manning's roughness coefficient and R is the hydraulic radius, S naught is the bed slope. So, in this case Manning's roughness coefficient or N, that is function of surface roughness, channel irregularity, stage and other parameters. In FPS system we write it in terms of V equal to 1.49 divided by N R to the power 2/3 S to the power half. What is the dimension of this quantity? Dimension of N is T L, that is time, L to the power minus 1/3, and in case of steady state incompressible flow condition we can write this Q equal to AV. So, discharge can be written as 1 by N A R to the power 2/3 S to the power half, and in this case Q is very sensitive to N. N is related to physical quantities like surface roughness, irregularity, channel irregularity, but the problem is the quantification of N is important in this case. So, in historical note the best fit formula was this one, then simplified it to R to the power x. You can see that x is varying, and intermediate version was this one, but dimensionally correct one is this full formula, but this intermediate version is much more popular. You can see the details from this website. This is Robert Manning. So, uh, roughness or smoothness, that depends on the nature of the surface of the channel, and for different types of natural channels or man-made channels you will find different values of N. So, if the cement plaster is there, so it has got value 0.011. This is untreated anide, this is 0.016. Wood, this is 0.012. Again concrete towel finish 0.012. Asphalt 0.013, and natural channels gravel bed 0.025, 0.024. So, you can see that for natural channels you have N value is higher compared to lined canal system, and N is equivalent to or value is almost comparable to 0.038 due to the power 1/6, where D is the mean size of the bed material, maybe this is D50. So, if we compare our uh, uh, equations, if we compare our equations, then we can see that from Manning's equation we have velocity equal to 1 by N R to the power 2/3 S to the power half, and Chassis equation we have V C R to the power half S naught to the power half. So, if we compare these two, then we can relate the Chassis coefficient to this uh, Manning's coefficient, and the relation is in terms of hydraulic radius. So, Now we'll define the term normal depth. Normal depth in case of this open channel flow. So, in uniform open channel flow, the flow depth is termed as normal depth. So, uniform flow, your flow depth is equal to normal depth. So, how to get normal depth value? If you know the velocity at any section, then uh, you can represent uh, that velocity and hydraulic radius and relate it using some nonlinear relationship, and if you solve it using calculator, and you can get the normal depth value. So, most simple thing is that you can calculate the discharge. So, discharge is A into V. Discharge is easily measurable quantity uh, in open channel sections. So, with this information, with Q, we can relate depth of flow and discharge, because in case of uniform flow, there will be constant slope. So, next term, computation of normal depth. So, how to compute this normal depth? In rectangular cross section, uh, we can represent the perimeter as a function of y, area as function of y. So, what is that? So, perimeter we can represent it as b plus 2y, 2y, two sides, and at bottom the width is there. So, area is b into y. So, how to get this yn or normal depth? Yn can be written as function of q. So, r we can represent it as a by p, which is b by b plus 2y, q as 1 by n a area, this r to the power 2/3. So, by by 2 plus 2y, this to the power 2/3, and s to the power half. If we solve it numerically, you can get the value of y, because in this case q is known, q is known. That means for a given discharge, you will get unique value of y. That means in this case, your quantities which are given are uh, q, n, which is Manning's roughness coefficient, S naught is the bed slope. That means three quantities are constant, q, n, S naught. Similarly, if we talk about trapezoidal section, again we need to represent this perimeter in terms of y, area in terms of y. So, perimeter, this is b. If 1 is to m1 is the slope of left side, then this will be uh, the side weighted length, and on this side the weighted length will be b into root over 1 plus m2 square. So, finally, what will be the your area? Area is by. which is the middle rectangular portion, and half m1y into y, which is m1y is the base width for this triangular portion and y is the depth of flow, and again y is the depth of flow, m2 y is the base width for this triangular portion. So, total area we can represent it like this, and top width again b plus y m1 plus y m2. So, from this relationship we can obtain the depth of flow or normal depth in case of open channel flow from Manning's equation for a given discharge, given Manning's roughness and slope value. So, what is the most economical cross section? Most economical cross section. Most economical open channel flow cross section. If we write this discharge based on Manning's equation, then you can write this as A r to the power 2/3 S naught to the power half for a given slope. For a given slope, the flow rate is proportional to A by P to the power 2/3. So, there are two conditions. If you have a large cross sectional area A, that will give high Q. Otherwise, if you have large weighted perimeter, P gives low Q. For most economical cross section, area should be maximum and P should be minimum at the same time. That means, in this case, area should be maximum and P should be minimum at the same time. Then only we can ensure that there is high Q which can be there in the a particular open channel flow cross section. So, the condition for maximum discharge is dq by dy equal to 0 or d by dy a r to the power 2/3 this is d by dy, we can represent it as a to the power 5 by 3 p to the power 2 by 3 equal to 0, and this is equivalent to d dy a to the power 5 by square, provided that in this case we have a and p greater than 0. That is why we can write it in terms of this equivalent form. So, in this case, if you consider that we have a problem where our area is constant, then if we can minimize the perimeter, that solves our problem. For a given cross sectional area, if we can reduce the perimeter, we can solve the same problem, which is hydraulically efficient. So, the condition for maximum open channel flow discharge under a fixed area is your dP by dy equal to 0. For rectangular cross section, for example, rectangular section, this P equal to A by y plus 2 by. In this case, this area is fixed, so area is constant. So, we can write it that this P by dpy equal to minus y square 2 equal to 0, or this is minus b into y by y square plus 2 equal to 0, or y equal to b by 2. That means, for rectangular cross section or hydraulically efficient cross section, this y or depth of flow should be just half of the bed width. If this is the bed width, this is your y. So, in this case y should be b by 2. We can see that depth of flow is just half of the bed width. If you have flow in compound channels, this is the most common situation that occurs in natural channels or man-made channels. This is the overbank section. Sometimes artificial man-made canals or channels are designed to designed to consider the flood situation, and if you have main channel and to or to consider the flood water, we can consider this overbank section. During flood events, overbank flows may occur, and generally there will be flow in main channels. We can divide it into this total cross sectional area into different parts, and the flow can be calculated based on the individual components that will calculate from the individual parts. So, flow in compound channels, let us say this is ith section, obviously the roughness that is present in the main channel will not be same as the overbank section or your embankment section, where you can regularly see the growth of grass. So, in this case uh, mm, we can calculate the individual velocity components as from our Manning's equation as 1 by Ni I by Pi is to the power half, and finally we can integrate this to get the discharge value for the cross section. In RH calculation, weighted parameter in contact with the actual channel boundary is used. This is important point because uh, weighted perimeter which is in contact with the actual boundary, channel boundary, is only used in this case. Now, we will consider unit level problems. So, let us consider the problem: a concrete lined trapezoidal canal has bed width of 3 meters and sides inclined at 45 degree to the horizontal. A bed slope of 1 in 1000 and Manning's roughness coefficient of 0.015 is there, and estimate the normal depth when the discharge is 20 cubic. So, from our calculation point of view, let us say that your Z is the slope side slope condition, that is 45 degree. So, obviously Z equal to 1 is to 1 slope, and area is B plus Z y into y. So, 3 plus y into y, this uh, perimeter equal to bed width plus 2 side slopes. So, 2 into yn plus 1 by z 1 plus z square. So, 3 plus 2 square root of 2, because z equals to 1 is to 1 slope is there. So, from flow rate for uniform flow can be written as from your Manning's equation, q equal to 1 by n, a r to the power 2/3 and s to the power half, and from there we can write that 1 by n a to the power 5 by 3 p to the power 2 by 3 in this form, and we can take gauge value, and by changing gauge value you can get the desired normal depth for the channel for given discharge n value and s value. Although n value is constant for the channel, you can vary the discharge and S naught or slope of the canal. At 20 cubic discharge, the normal depth is 1.848 meters. Second problem, this is related to again trapezoidal section. So, calculate hydraulically efficient cross section for trapezoidal section of bottom B and side slope M horizontal and 1 vertical, keeping A and M constant. That means again keeping area constant and slope side slopes constant, we can solve this problem. Their area of the trapezoid is B plus My. In this case, area of the trapezoid, that is and depth of flow is y. This is b. So area of the trapezoid, that is b plus this is m, side slope is m. So this is 2 into half area. So this is y into base is m into y. So b plus by into my square. So b we can write it as a divided by y minus my. Again weighted perimeter equal to P equal to b plus 2y m square plus 1. This is a y minus my. This is in place of b plus 2y m square plus 1. If we differentiate it dp by dy, then minus a y square minus m plus 2 m square plus 1 equal to 0, or area is 2 m square plus 1 minus m y square. In this case, if we substitute this y e value or efficient depth value in this equation, we can get the value of b, and if you utilize the same thing here, we can get the value of uh, p. So substituting that area, we can get b equal to 2 m square plus 1 minus m y e minus m y e, and this one we can write it as m square plus 1 minus m y e. Perimeter, this is 2 m square plus 1 minus m y e, or hydraulic radius is 2 m square 1 minus m y square minus m y e equal to y e by 2. So in this case, we can see that hydraulic radius is just half of the flow depth, and in this case hydraulically efficient trapezoidal section having properties computed previously is shown in the following figure. So in this one, this is y e, this is b e, this is 1:m, this is o t, which is perpendicular. So os equal to y e, o t which is perpendicular on this surface, we can write it as if this slope, or this slope is or this angle is theta, then we can write it as or sin theta, or or sin theta is 1 by root over 1 plus m square, or or equal to y 1 plus m square. That means OT and OS, these two quantities are same. Thus, the hydraulically efficient trapezoidal section has a semicircle inscribed in it. So, with this I am ending this unit. So, if you have any question or queries, you can. Okay, what we'll do, we'll start the next unit with this questions. That means in the next session we'll start by answering these questions. Okay, thank you.